Welcome to the Foundry by Forge College. Today, we're diving into an explainer on a really fascinating and honestly kind of frustrating topic: contemporary challenges in Bitcoin mining. Now, if you've been following along in our Bitcoin fundamentals track, you know we've already covered the theory, the core processes, and the underlying math. But today, we're stepping completely out of that theoretical vacuum and diving headfirst into the messy, unpredictable real world. So get comfortable, because we are going to map out the exact challenges that can literally make or break a mining operation.
First off, I really have to congratulate you all. In our previous lesson, Strategies for Improving Mining Efficiency, you did an incredible job. You ran the benchmarking results, built out your operational checklists, and optimized those lab setups to absolute perfection. In that ideal lab scenario, the temperature is always right, the power literally never blinks, and your machines just hum along beautifully. Well, welcome to the chaotic reality of the real world. Out here, external pressures absolutely do not care about your perfect lab conditions.
To navigate all this chaos, we're going to need a master engineering blueprint. Today, we'll quickly run through a reality check, hardware and energy dynamics, supply chain bottlenecks, grid scalability, regulation, and finally, a practical site viability workflow. Let's get right to it.
Section 1. The Mining Reality Check.
So all those brilliant efficiency gains you squeezed out back in the lab? Yeah, they can get completely swallowed whole by external constraints out here. Think of these constraints as the 5 major dragons our heroic miner has to battle. You've got energy dynamics fluctuating wildly, supply chains causing massive delays, scalability issues with local grids, regulation throwing up legal brick walls, and the relentless pace of tech and future trends. You have to defeat, or at least carefully manage, all 5 of these if you want to survive out there.
Moving on to Section 2. Hardware and Energy Dynamics. Make no mistake, energy is the single largest recurring expense in any mining operation. It is the lifeblood, and it's exactly where your margins are made or lost on a daily basis. The absolute ultimate metric you need to watch is your cost per terahash per second. In the reading material, there's a Python script called Energy Cost Metrics that calculates this. Now, don't let the word Python scare you. We're really just demystifying the math here. It simply takes the upfront money you spent on the rig, spreads it out over time, and adds your daily power bill, normalizing the whole thing to the actual computing power you generate.
The logic behind that script actually relies on 5 pretty simple math inputs for our blueprint. You take your upfront CapEx, your hash rate, your power draw, your electricity price, and your days of operation. You just plug these variables in, it takes all the guesswork out of the equation and lets you programmatically test different scenarios, like say, running machines at night when power might be cheaper, without getting bogged down in actual coding syntax. It's really all about making informed, purely mathematical decisions.
All right, Section 3, Supply Chain Bottlenecks.
Let's zoom out from the individual machine to the facility level. What happens when things physically break? We have to talk about lead time. Lead time is exactly what it sounds like. It's the delay between you hitting order on a replacement part and it actually showing up at your loading dock. Imagine ordering a pizza on a Friday night, right? But the delivery guy says, "Great, I'll be there in 3 to 4 months." That is the harsh reality of specialized mining hardware.
120 days. No joke. That is a very real, severe vendor lead time in this industry right now. If you plug a 120-day lead time into our simulation exercise, you literally watch operational downtime skyrocket the second your spare parts run out. Your extremely expensive machines sit there, perfectly configured, doing absolutely nothing but collecting dust and losing you money for 4 straight months.
So what's the fix? The crucial point is this: you cannot just rely on perfectly timed deliveries. The concrete solution, the only real protection for your operation's hardware resilience, is to hold spare parts locally and absolutely diversify your suppliers. And yeah, I know, holding inventory ties up your capital, but as our simulation proves, the cost of a blown power supply is basically nothing compared to the massive cost of 120 days of zero hashing.
Up next, Section 4, Grid Limits and Scalability. So you've got the machines, right? You've got the spares, but can the local electrical grid actually handle you? This brings us to a frankly terrifying word for miners: curtailment. Curtailment is basically the grid pulling the plug on your operation right when you need the power most. Imagine it's a freezing winter, everyone in the city turns on their heaters, the grid gets super stressed out, and the local grid operator calls you up and says, "Hey, turn your machines off right now. You don't have a choice." If you set up shop in a spot with, say, a 20% curtailment rate during peak seasons, you are losing a massive chunk of your operational time. Doing the math on that, this can literally double your effective energy cost per useful hashing hour. Why? Because your rent, your labor, your capital depreciation, all those expenses just keep ticking away even when the grid forces your machines to sleep.
Which brings us to Section 5, navigating regulatory red tape.
Now we got to look at the legal jurisdiction. You can engineer the absolute perfect site, but if the local government doesn't want you there, you're done. You have to look at zoning classifications, massive electrical build permits, and super strict noise limits. Honestly, compare local regulators and zoning boards to an incredibly strict homeowners association that's suddenly dealing with the noise of an industrial lawnmower running 24/7. They will scrutinize your cooling fans, your power draw, and every single one of your permits.
The real secret sauce to handling all of this is that qualitative risks must be turned into quantitative inputs. Take something squishy like regulatory risk and turn it into a hard number. Permit lead time in days. What's your mitigation? Early engagement. Take scalability and measure it in grid kilowatt capacity. Mitigation? Phased deployment. You take supply chain and look at vendor lead time. The mitigation? Hold spares. You are essentially translating abstract fears into concrete, actionable numbers.
Finally, Section 6, the site viability workflow.
Look, if you are putting together a capstone report or actually out there deploying millions of dollars, you need a practical, repeatable workflow for assessing candidate sites. You gather the site data, map the regulations, assess the technical scalability of the grid, calculate your vendor exposure and supply chain risks, and then you synthesize it all into an action plan. This is your ultimate troubleshooting workflow.
And let me really emphasize something here. For step 1, you must gather hard empirical numbers first. What is the precise grid connection capacity in kilowatt? What are the exact time of use tariffs? What's the 5-year curtailment history look like? You absolutely have to augment your electricity pricing models with these hard facts before you commit a single dollar of capital.
Finally, in Step 5, synthesis, you take all that data and create a matrix of risks, mapping out likelihood versus impact. This matrix is what triggers your specific mitigation tasks. By the way, if you find yourself really geeking out over this kind of high-level strategic planning, you should definitely check out some of the other courses and programs at Forge College. There is some genuinely fantastic material in the curriculum on building out advanced risk matrices and operational strategy.
Let's quickly summarize our key takeaways for today. First, always convert qualitative risks to hard numbers. Second, match your operational tactics to your strategic exposure. And third, build repeatable assessment workflows. Remember, those short-term efficiency optimizations you made in the lab only actually matter if you can survive the external constraints of the real world.
I want to leave you with this final thought to ponder before our next session. How will local statutes, ordinances, and policy levers impact your specific site's viability? Keep that in the back of your mind because it perfectly sets up our upcoming lesson, Regulatory Landscape and Policy Responses. Thank you so much for hanging out with me today. For more deep dives into Web3 topics and to keep exploring this stuff, be sure to visit forge.college to continue your learning journey. See you in the next explainer.